Good afternoon, everybody. Welcome to the 11:30 session here in Pod 4. We have Chief Executive Officer Simon Irish representing Terrestrial Energy. Simon, the floor is yours.
Yeah, thank you very much. So, we've got the sound going? Yes, I think we have. Okay. Well, certainly, thanks very much for this opportunity to tell you a little bit about terrestrial energy and the small modular reactor technology that we've been developing for the last 12 years. So we're developing this as a technology innovator in the context of a market circumstances. The innovator has to understand market circumstances, understand market needs, and I think this slide represents the clear market need, and that is when we formed the business 12 years ago, we recognized the ineluctable necessity, if we are to grow energy supply next decade beyond, and grow energy supply with secure, reliable, clean energy. If you look at that demand curve looking forward, it can only possibly be met with a massive expansion of nuclear energy supply. And that is what is interesting, very interesting for us as a company, is whilst we set up the company on a first principles basis, recognizing this is going to happen, okay, we did so 12 years ago, and if you imagine, you know what was happening 12 years ago, nuclear was not particularly popular. But nonetheless, that unpopularity disguised a deep, deep necessity, if you like, a gravity well into which reality would have to fall, and that is the reality that we need to expand nuclear energy supply and do it quickly and do it at great scale. So I think you see this in the headlines now, that you look at the announcements by companies, I think quite recently, big tech companies, even yesterday, came together and said we recognize that for our needs, we need a massive expansion of nuclear energy supply. Governments, advanced industrial economies over the last 2 years have been saying the same thing too. So this is our market context, and this is why we set up the business 12 years ago. So this slide shows what we've been doing. Our plant is called the Integral Molten Salt Reactor Power Plant. There's a picture of it in the top right-hand corner. That plant is distinguished in a couple of key regards. It consists of two parts. The first part, Part A, consists of nuclear systems. These are modular and standardized. That's necessary for two reasons. Firstly, economics. Okay, what you want to be able to do, we're not looking to build 1, 2, 3, 4 of these things. We're looking to deploy 10, 20, 30, 40, 50, 100, 200, 300. So modularity is very important. The concept of manufacturing a key component in a factory setting, shipping it to site, and assembling those two key components on site. Now, this is also called an SMR, small modular reactor. Okay, I would just a cautionary note: many things that sit under the press banner of SMRs are neither small nor modular. So a little bit of a cautionary note on this sort of ubiquitous term called SMRs. I would say that the action in the SMR term that you see in the press, all the action is not in the small or the modular, it's all in the R. And the reason I say that is that the R is the reactor technology. The last slide spoke about energy supply, nuclear energy. This is nuclear technology. The big distinction between nuclear energy and the machine you use to harness nuclear energy to deliver it commercially. So this is the machine that's using nuclear energy to deliver it for a productive commercial purpose. And if you looked at the number of machines that you see today under the banner SMR, there is a rich kaleidoscope of many, many different technologies. Some of them are called Generation IV, light water reactors, boiling water reactors, and within the Generation IV category, you have sodium fast reactors, high temperature gas reactors. This is a molten salt reactor. So I'm just saying there's tremendous diversity here, and within that diversity of technology and also design, it's not just about the reactor, it's how you design the power plant too. You have the possibility that some of those designs and some of those technologies can address what the principal problem for nuclear technology is today. And my background is I came quite late in my career to the nuclear industry. My background previously was in financial services. And I see things through the prism of capital. The problem for nuclear energy today is a very simple economic point. The nuclear machine today, in its current design with the current reactor technology at the heart of it, is unaffordable. That's nuclear energy's problem. That's it. So this is our power plant design. But part A, small modular nuclear systems that are regulated. On the regulatory front, we have cleared a couple of very material hurdles in terms of regulatory scrutiny. We spent about $100 million in 5 years with a Canadian regulator, and they summed up their opinion and responded to their review in April 2023. And we've been engaged with the US NRC since 2017. The bit behind part B is a very interesting feature of our design. That sits outside the nuclear regulatory envelope. And sitting outside the nuclear regulatory envelope, it is not regulated as a nuclear system. These are standard industrial systems. So what it means is that you can quickly adapt and customize your energy, your primary energy stream, which is heat, to the needs of your customer, which is C. Now, C today, and this is if you looked at nuclear energy demand today, it's very different compared to the past. In the past, nuclear energy demand is utilities, regulated grids, and that's nuclear energy demand. Nuclear energy demand now is associated with many other industrials that are seeking nuclear energy to supply what they perceive to be the essential strategic energy commodity that they need to execute their business plans looking forward in the 2030s. And that is the ability to bring gigawatt scale clean, firm generation to a particular site. So the paradigm for our plant and also other SMRs is a totally new paradigm in the supply of industrial energy. I would say, since the start of probably the Industrial Revolution would not be hyperbole. And that is, with this A-B-C combination, you have the ability to bring gigawatt scale, clean, firm heat and power, very close, co-located, near-located to a point of massive industrial demand, whether it's a chemical plant, a petrochemical plant, a data center, and so forth. This is not dependent on the grid. This is not dependent on natural gas pipeline. Okay. So all those other technologies have a constraint, which is a transmission constraint. And we're living in a world where developing transmission, whether it's the distribution of natural gas or distribution of power, that is the bottleneck. Can this system scale and expand fast enough to meet the demand for electricity we're seeing going forward? Many of the guys looking forward strategically in that box C, the big tech companies, the chemical companies and so forth, recognize that it's probably not going to happen. You need to bring it to site. You need a smaller modular power plant that can be co-located near site, delivering the essential ingredient, economic ingredient, which is cost competitive heat and power, maybe just power, maybe just heat, maybe both, and do it, and power which is zero carbon, this is nuclear, and power that's reliable. Nuclear is very reliable. So before I move on, just a couple other points as well. Our primary energy commodity from our nuclear system, from our nuclear plant, the A piece, is high quality heat. This is best in class in the advanced reactor space, and this is transformatively different compared to nuclear technology that's been deployed commercially over the last 65 years. 585 is high quality heat. With 585 degree heat, you can match the same, you can have a very efficient steam Rankine cycle. Or, if you choose, you can send it straight to the chemical plant, petrochemical plant that needs process heat to make many of the materials of the modern age that require thermal energy as a primary input. So the reason we can do all this and design a nuclear power plant to match the very particular needs of nuclear energy demand that we see in front of us, which is different compared to nuclear energy demand previously, is because we're using a molten salt reactor. Molten salt reactors have been around for 70 years. This is not new technology. What's new is you have a private company that is seeking to commercialize it. That's what's new. The technology isn't new. So molten salt reactor technology over the last, since it was first demonstrated over half a century ago, is recognized that those that understand this technology as delivering a distinct set of operating characteristics that make this technology extraordinarily exciting if you're looking to transform the economic position of nuclear energy supply, the affordability of the nuclear power plant. And those three characteristics, these are the only characteristics you get from multi-salt reactors. High temperature thermal energy supply, low pressure operation, and high inherent safety. Those are powerful economic virtues, particularly the high temperature heat supply as well. You have a very efficient steam Rankine cycle. That compares to where legacy nuclear is, the current nuclear machine that's delivering nuclear energy. It's been a workhorse for many years, but it has a fundamental constraint, and it will never break those bonds. And that's associated with its three operating characteristics of low temperature thermal energy supply. You have an inefficient steam Rankine cycle and a very costly steam turbine, which is a nuclear turbine with a long lead time. It's a very specialist bit of kit, not the case with ours. High temperature operation, makes it very difficult for engineers doing this. High temperature operation and the requirement of high active safety. We don't have a control rod, for instance. You don't have a guy upstairs in a control room running control rod up and down. This is inherently controlled. So these are economic penalties, economic weights. You cannot remove those economic weights from legacy nuclear, which is light water reactors, and also other reactor systems of that era as well, heavy water reactors too. So with those three operating characteristics, a couple of really big commercial consequences. For us, with high capital efficiency, high capital efficiency, high energy density too. We can have a small power plant, so small unit size, right size for market need. The nature of nuclear energy demand today has to be right sized, not these gargantuan nuclear machines that we've built for the last 50 years. So it's right sized. It supports the need for distributed generation, and we can also do a conventional mode of deployment, simply on grid and supplying grid. That's possible as well. But we can also provide nuclear-generated industrial cogeneration, high-quality heat and power as well. And that's to do with the capital efficiency and those three operating characteristics. The operating characteristics of legacy nuclear confine it to its current mode of deployment, which is massive plant with project risk that requires massive government sponsorship and leadership. It will still happen. It'll still play a role in many markets. But if you want to transform nuclear energy supply, if you want to meet the requirements of nuclear energy demand going forward, which is potentially enormous, these are the type of operating characteristics you need in a nuclear power plant. It has to be small and modular. It has to be highly economic, and you get those economies from these operating characteristics. So these are sort of putting some numbers on it, going back to the heat point, because this is what is transformative about it: high quality heat, super efficient steam Rankine cycle, as opposed to heat at 270 or 299. So we're 44% more thermally efficient compared to a conventional nuclear power plant. And that's a 50% improvement in efficiency. Now, for an industrial process, which is 50% more efficient, that is not a marginal improvement in any industrial process. 50% efficiency gains is transformative. We anticipate that we'll be able to deliver thermal energy at about 8.6 MMBTU, electricity just under 70. The plant itself generates about just over 800 megawatt thermal, just under 400 megawatt electrical, if you choose to use all that thermal energy for electric power generation, but you can split it up in any way you want. The plant exists for 70 years. The last point as well is we use standard nuclear fuel. Very important from a supply chain perspective, very important from a regulatory perspective, very important when your engagement to customers now, to the market now, is not about this is how we're going to build the first plant. That's important, but not sufficient to your proposal. Your proposal is this is how we deliver a fleet, 10, 20, 30, 40, and do so in the 2030s. So on the nuclear fuel side, our unique position in the market today sits on the intersection of two really important roads. One is the requirement to deliver high quality heat with all the economic virtues that go with it. And the second is to do it with standard nuclear fuel. Terrestrial energy sits singly, uniquely on the intersection of those two roads. So the plant lasts for 50 years, and as I said, this technology is not new. Okay, what's new here is you've got a private sector company that is seeking now to commercialize it, and we've been going about 12 years. These are our markets. So with that flexibility, both in siting, because we're a small modular reactor, and the ability to customize for heat and power to the requirements of C, the customer, we can service many markets in a very different way. This is not the, if you like, the service addressable market you would see for a light water reactor or legacy nuclear. So data centers, industrial plant requiring heat and power, yes, we do this very well. On-grid power generation in a conventional setting for nuclear, we do that very well. And you've also got those future markets that could be gargantuan. If you are to generate green fuels and green materials, you need to have a massive industrial plant, a single point where there is gigawatt scale demand for clean, firm power. If it's not clean, you don't have green. Okay? So our ability to service that future market, which may consist of transport fuels, hydrogen or ammonia transport fuels, is a capability of our technology and our power plant design. So thank you very much for listening. If I've timed that correctly, we've got a few moments for questions.
So we're going to open the floor for questions. Please raise your hand. I'll bring the microphone and get started.
So thanks for that. Kanye from Nigeria LNG. You talked about the reliability of the plant. For a Tier 4 data center, would they have to think about any redundancy in terms of any failures, or is this sufficient?
Well, the reliability, I'm not entirely familiar with the Tier 4 standard, but let's say I assume it's that super high standard of reliability. For any power generation technology, you only get that reliability at a system level. So we would anticipate, well, achieving a very high reliability by, yes, in an island generation mode, we would not get that reliability, and no one would in island generation mode. But we can get that through the integration of natural gas into the back end of our plant. So you've got that part B is dual fuel supply. Natural gas when the nuclear system's down, and when the nuclear systems are up, you run the nuclear piece. You're probably going to have to be grid connected, or you have a site where you have sort of 6 of these plants, and you will probably in island generation mode have sufficient redundancy to achieve the thank you. Good point.
Thank you for a very interesting presentation. I have 2 questions. The first one, you didn't give much details about the technology inside of it, but because you have 5% uranium, I suppose it's a thermal reactor, maybe graphite moderated or some with moderation. Yes. We had a very nice presentation from Kairos on their development plans, so technology development. Is there anything you can tell us about this? Because as far as I know, there is no such existing technology on the market, so it has to be developed. Yeah. That's what you do. So. Yeah. And my second question is how in the M for modular, how do you? It's a quite large plant, so how modularity is taken into account?
Yeah. So I'll take your first question first. You may have to remind me about the second question first. You may have to remind me about it first. But on the modularity piece, what's important about modularity is you have, if you want the economics of modularity, you need to have a nuclear system that's got a high energy density. Like water reactors have, and I always find this a bit of an amusing thought, energy density was essential for in terms of the origin story of the light water reactor. Back of a sub, you haven't got much space. Volumetric has to be energy dense, and it can't be too heavy, but you can't sing the thing. So light water reactors, to their credit, do modularity quite well. Molten salt reactors, to their credit, also do modularity in the Generation IV space equally well, because you can have a very energy dense system, a sufficiently energy dense system. We're equivalent energy densities like water reactor. So you can have relatively small components that you can manufacture and put on a truck, a rail car, and take to site. That connection between energy density, transportability, and site assembly, those connections don't exist for quite a few things that are called just generally by the press small modular reactors. You have to remind me about the first question.
The first question was on the technology development side.
Yeah. So we've been going 12 years. There's a group in the sector that's probably started at the same vintage, and In terms of our development, our position is the company that is classically commercializing the molten salt reactor that was demonstrated at Oak Ridge National Lab in the late 60s. In fact, the chief engineer on that system was part of our design team for the first 5 years of the company's life. So that's the one that's been demonstrated, and we're commercializing it.
So there won't be any critical markup or any such a thing. Critical markup, like a non-power.
But I think if you look at what the sector's doing, everyone is, in that lead peloton of 6 to 8 companies today, everyone is to some extent, there's a sort of quite a generic, project plan to first deployment. You will have to, at a system level, demonstrate the performance of critical systems. So your thermodynamic test rig, your neutronic test rig, and everyone will be doing this type of thing. So that's what we'll be doing, and that's part of our development plan. We expect to make announcements on this probably in the next 6 months. Yep, thank you. In terms of where we're going to site them. Yeah.
Any additional questions?
Maybe this was implied by your previous answer, but when do you foresee deployment of the first
plant?
Yeah.
Yeah, that's a.
And do you have? I mean, do you have a partner that you're already thinking
Yes.
about?
Okay. We announced a couple of weeks back, and this is a project we can talk about. We've got quite a few projects, but it's important we're able to talk publicly about a project, a very credible project. So we responded to a formal solicitation in the nuclear tech sector by Texas A&M, a public university in Texas. Obviously, I think many people are aware of that, and it's expressing, I think, what Governor Abbott and the legislator in Austin wish to achieve for Texas, namely Texas as a destination state for nuclear tech and the destination state for nuclear. I think they're doing that job very well indeed. We prepared a proposal, assembled a very impressive consortium with constructors, operators, and suppliers. We were selected, and we're moving forward with Texas A&M. It's a very credible site. It's a very incredible counterparty. So we've got a site. That site has a requirement, or the owner of that site has a requirement for 1 gigawatt of generation, looking forward 10 years. Texas A&M is the leading nuclear engineering school in the country, probably the most credentialed issuer of an RFP to the nuclear tech sector, given their capabilities. They've selected, what's interesting, they've selected out of the 4 companies, 3 are molten salt reactor technologies, to the point that it's molten salt reactor technologies with those 3 operating characteristics that have the capability of totally transforming the affordability and economics of nuclear power generation. So that's a project we can talk about. I think it's very exciting. It will, by construction, with our association with Texas A&M, I think it will very likely become a benchmark project in Texas. And at a national level, I think it will be an important project, national level too. So it's a super exciting time, for us with our project plans.
So in terms of like the timeline, for like when do you expect to have steel on the ground?
Yes, I'll be sort of quite generic about this,
yeah.
if you wouldn't mind. I think the timeline, and this is technology independent. If you've got a nuclear project, you can. It's a 10-year project. Okay, this is where you select the site, start doing the site characterization work, start assembling the team to do the license preparation. If you looked at on a Gantt chart, the elements necessary to complete the project, you're doing under 10 years for the first plant. It's a 10-year project, the first plant. Yeah.
Any last questions for Simon?
This is just a brief follow-up on the A&M conversation. So there are 4 separate sites with 4 technologies. Terrestrial Energy is one of them.
Terrestrial is one of them, yes.
Nice.
It's a 2,000-acre site with probably, it's possible it could extend as well. So it's got plenty of capacity to accommodate small and modular reactors. I can't comment, obviously, on the plans. I've got no privileged information on what the other 3 are looking to do.
Okay.
But from our perspective, we're moving ahead with, our engagement with Texas A&M on the site.
So, but ultimately, one design will be down selected.
No, they're interested in all 4.
Oh wow.
Yeah. They serve different markets. Yeah.
Anything else? Okay. Please join me in thanking Simon.
Thank you very much.